All right. Howdy, everyone. Welcome to TAMU Datathon 2023. My name is Eric Nunez. I am a Challenges Officer for this year's Datathon, and it is my pleasure to bring you and your team a series of videos to be able to help you gain a fundamental knowledge of data science and machine learning techniques. And so, the objective of this video is to be able to go over the Python library NumPy. So, NumPy is very useful for both mathematical operations as well as doing storing arrays and matrices. And so by the end of this video, I'll be able to show off how you can create your own matrices and perform a bunch of mathematical computations, as well as showing off some of the different functions that you can see with NumPy. So note that this video is not completely thorough. If you're more interested, I do recommend Googling the NumPy documentation, as well as looking up any other commands that you might be interested in. And so this notebook, as well as many others, will be available to you for you to be able to access and run on your own. This is running on a Google Colab environment, and so you can access this notebook and many more at tx.ag/td23 notebooks. Once again, that's tx.ag/td23 notebooks. And I'll also go ahead and leave a link in the description to be able to allow you and your team to be able to access this and run it on your own. So without further ado, let's go ahead and get started. So first thing we want to do is be able to import our libraries. Today we'll focus on NumPy. We'll talk about pandas in another video, but for now, let's focus on NumPy. So whenever we import NumPy, we want to typically include this clause as NP. And the reason we want to do that is that it's just standard practice. It just shortens it, and most data scientists already use, and they like having this NP rather than just having to call NumPy. So what this does is pretty much takes all the functions and modules of NumPy and it imports it into your local environment, and this will be pretty useful for us. Similar thing for pandas. We import pandas and then we import as PD. And so pretty much anytime we're going to call a function, a NumPy function, we'll often see np dot something. Or if we're calling a pandas function, we might see pd dot something. And so these two are just standard practice. I would definitely recommend importing NumPy as np and pandas as pd. So let's go ahead and jump straight into it. And so NumPy is a Python library that allows for more complex mathematical computations and allows you to create large-scale arrays and matrices, like I said. The name comes from numerical Python extensions, so numerical Python extensions. It's been around since like 2005, but it really has been gaining steam since like the mid-2010s-ish. And there are many reasons why you want to use NumPy instead of just traditional Python lists and arrays. For starters, NumPy's base is actually built in C. And the reason for that is because, for those that don't know, Python runs historically bad. Like, it runs really slow compared to a bunch of other programming languages. It's really nice to be able to visualize, and it's like very easy to code in, but that comes at the trade-off of like being a much slower language than languages like C, C++, C#, and Java. And so because NumPy's base is built in C and then later implemented, like repurposed for Python, it runs a lot faster than your typical Python array or list. And also whenever we perform experimental wise or elemental wise or just any mathematical operations using these large scale vectors, these large-scale arrays, it's much easier and faster to do it with a NumPy array than it is with a normal Python list. Also, there's a benefit that NumPy arrays are typically more memory efficient than the typical Python list. So those are some of the big advantages of why we would want to use NumPy over Python. And so let's go ahead and run a sample. So we can go ahead and see that we have a one-dimensional array, and the reason we call it one-dimensional array is because you can actually scale arrays to be able to contain arrays within arrays. So you can think of a matrix or a 2D array or 2D array as an array comprised of arrays. We'll explore more of this with this bottom example down here. So we see we have like our outer array over here, and then we have some inner array. So like we have this inner array of 1, 2, 3, inner array of 4, 5, 6, inner array of 7, 8, 9. And so you can consider a two-dimensional array to be just an array of arrays, a three-dimensional array to be an array of arrays of arrays. And so we can see that when we run this, this is one dimension. And then if we go ahead and we can go ahead and like get the first element by calling a one-dimensional array. We put these square brackets around it, and then we put 0. This is an example of indexing, and do note that whenever it comes to NumPy or just most Python and many programming languages in general, if you're using arrays, lists, or the equivalents in many programming languages, they will be what's called zero-based indexed. And what that means is that whenever you want to call something, the index or like the value that it's assigned to, it will start at 0 and not 1. And so whenever we call one-dimensional array at index 0, that's technically meaning get the first element of this array right here. And so we see that we get 1, and then we print the shape, and it's a one-dimensional array with 4 elements. Similarly, with our 2D array, we can go ahead and run this. You see that it's displayed almost in like a matrix kind of form. One thing I will warn is that if you do create like a 2D array, make sure that all the elements have, all the inner elements have roughly the same length. Because if you have a case where it's like this one has like three elements inside, this has 3 elements inside, and this has 2, then it can get really wonky, and it's not exactly recommended. And typically we want to do this since NumPy is great to be able to represent matrices. If you've ever taken a linear algebra class or a diffie-q class, then this will be pretty useful for you. We can also call this similar thing like where we have two-dimensional array at index 0, albeit this will get the first item within this whole array. But then that doesn't mean that we're going to get the first item overall. Instead, what's going to happen is that it's going to get the first item, and because we considered this inner array to be one item itself, then it's going to get that item. And so that's why with a two-dimensional array, we return this. If you want to get a specific element, then what we got to do is we got to call the row in which it's in, and then the column in which we want. So in this case, we say the row at index 0, and then column at index 2. And so we see that this corresponds to row 0, and then based on columns, aka the elements inside the inner arrays, we have index 0, index 1, index 2. And that's why whenever we call a two-dimensional array at 0 and 2, we return 3. And then similarly, if we call two-dimensional array shape, we see it's a two-dimensional array with a 3 by 3. And there's also this code for three-dimensional array. I won't spend too much time on this. If you get the idea behind one-dimensional and two-dimensional arrays, then you should be able to get the idea behind third-dimensional arrays. I'll just point out that three-dimensional arrays and higher typically aren't common in data science. Not to say that, oh, you won't see it, but typically, whenever we want to represent data, for example, if you open up an Excel file, you can represent that in 2 dimensions. And so it's not that common that you'll see three-dimensional arrays or any arrays with greater dimensionality. So just pointing that out there. You can also get the number of dimensions of an array by calling the name of the array .ndim, and this will just get the dimensions of that array. Pretty simple. We can also create arrays based on different functions that will already do the heavy lifting for us. So you see over here, we actually manually defined all these, but what we would want to do over here is these functions can actually do create and like just put in values in for us already. So if we call np.zeros, this will return an array or matrix of consisting of all zeros. One thing that is worth noting is that the parameter that is taken in for many of these functions is actually what's known as a tuple. So a tuple is like a pair or just a multiple ordered set of elements. And so what this does is that, and so the number of elements within the tuple corresponds to the number of dimensions that we have. So in this case, because we have two elements within our tuple, then this is going to be a two-dimensional array. And it's going to be a two-dimensional array of 2 rows and 2 columns. Similarly, we have np0s, which fills it in with zeros. np1s, it fills it in with ones. It's pretty trivial. np.full, it actually takes in 2 parameters. The first is the tuple that specifies the shape, so like the dimensions and all that. And the second parameter is the value in which you're going to fill it in with. We have np.I. This will actually return a 2D matrix, like a 2D identity matrix. If you haven't taken linear algebra, this will be a concept that you'll learn within that class. It's pretty useful for some ML theory, albeit, at least for these videos, we're not going to dive too much into the theory. We're going to be more so talking about the implementation. If you are interested in that, then I would strongly recommend considering taking a stat minor or a CS major or vice versa. But fun fact, the reason why we call this np.I, like with humans, is that the identity matrix within linear algebra is represented by the letter I. And so the people who developed this, they just got a little bit cheeky and said, oh, we'll just call it I, like the human eye. It's, they got a sense of humor. And then we got np.random.random, and then we specify our shape that we want, and this will give us a bunch of random values between 0 and 1. And I'm actually going to go ahead and actually change this to, say, 2 by 5, just to show off, and we'll change this one to, let's just change it to a one-dimensional array, see what happens. So we see over here that we got a 2 by 2 matrix of zeros, and then we got a one-dimensional array with 2 elements inside. Both of them are 1s. We got this one where it's filled with 7s. Again, that's because we specified the 7 up here. This returns an identity matrix. Again, I wouldn't worry about it too much for at least theory-wise for this hackathon. And then we got random, which generates a bunch of random values from 0 and 1. Perfect. And then we have arrange and linspace. So arrange works very similar to the range function within Python, if you're familiar with that. Do note that with arrange, as well as just regular range, the start value is inclusive, but the stop value is exclusive, meaning that whenever you do this, it will count the start value, but it won't count the stop. So in this case, we'll go ahead and run this, and we see that when we generate this, we pretty much get a list of items, and then we print out each item. And so we print out from the range of 3 between 12, and we get every third item. We get 3, 6, 9, and even though we specify 12 over here, we don't get 12. And again, that's because the stop value is exclusive. We do not count it. And then we have linspace. This works in a similar fashion, albeit instead of having an increment value, which will keep going up and up, we will actually have a start and stop value, and it will return a certain amount of evenly spaced numbers between start and stop, both of them being inclusive. And so if we go ahead and run this, we see that we get a list of values over here of 0.0, 0.125, 0.25, 0.375. And so if you're aware of math, you'll actually realize that this is equal to 0 over 8, 1 over 8, 2 over 8, 3 over 8, so on and so forth. And if you count the number of these values, you'll see that they all come out to 9. And so that is pretty interesting, and you can tinker around with this as much as you like. Arrange and linspace are particularly useful if you want to be able to quickly generate a list of numbers that are either like counting wise, or if you want to be able to generate numbers within a specified range and have them evenly split. This is particularly useful if you're going to be able to develop a graph and you don't have an index to base off of, and you don't want to be able to just and you don't want to just run a you don't want to like type out 3, 6, 9, 12, 15, 18, and so on and so forth. We have distributions over here. There are many different kinds of distributions. If you've taken a statistics class, then you'll definitely be a lot familiar with that. But for today, we'll just talk about the binomial distribution, just because it's the most simple. If you are curious about some of these other ones, you're more than free to be able to look up the NumPy documentation as you like. But we'll talk about the binomial distribution since, it's a classic. We have this command over here called np.random.seed. What this does is that the thing with computers is that whenever you say to generate random numbers, it is actually not random. It is what we call pseudo-random. It simulates randomness, and to us, it looks like randomness, but the computer has algorithms to be able to just compute all these values. And so what seed does is that it'll actually go ahead and say, you can think of it like the seed in Minecraft. You know how whenever you type in a seed for world generation, and then you can go on a completely different computer on a completely different country, type in that same seed, and you'll get the exact same world. Yeah, it works in a similar fashion over here. So what this does is that I can run this as many times as I want, and I will always get this value of 4. So 4, 4, 4, 4, 4, 4, so on and so forth. But as soon as I remove this, then you'll see that I get a bunch of different values. So let's go ahead and add that back. And you see that we introduced this binomial function over here. And so what this actually does is that we have this first parameter, which is the number of trials that we want to perform, versus a p-value, also known as the probability that something occurs. And so in this case, we see that we have 10 and 0.5. 0.5 I just said because it pretty much simulates something as even as, say, a coin toss. And so what this will do is that this is pretty much kind of a way to be able to say, like, oh, if you have a question like, oh, if I'm going to flip a coin 10 times, what's the likelihood that I'm going to get heads, like out of all of those tries? And then in this simulation, we ended up getting 4 heads and 6 tails. And we can change this as we like. So like, for example, if I were to increase this value, decrease this to 0.25, we're less likely to see larger values. And so, for example, we see 2, 2, 2, 2. It all concentrates down like towards 2. 2. I imagine we're going to get, sorry, I forgot that we had the seed over here. So we have 5, 3, 3, 1, 1, 1, 4, so on and so forth. And we can generate this as many times, and even though there are 10 trials, we see that the largest number of probability that we got was 5, and even then that was fairly lucky. We'd have to be absolute wizards to be able to get 10 out of 10 with a 0.25. You can actually run the code several times by introducing a third parameter. And so what this will do is this says okay, so given 10 events with this probability, what's the likelihood of that happening? And then generate, say, what is that? 100,000 trials of this. So I can go ahead and print this. Note that the for loop down here does a very similar thing, albeit it is a little bit unnecessary considering that we have this parameter that just already does it for us. So in this case, we see that we get something like 2, 8, 7, 6, 4, 5, 1, 7, 4, yada 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 all the way to 7, 5, 2. So this is the equivalent of saying in the first trial, we flip a coin 10 times and we got heads twice. In the second trial, we flipped a coin 10 times and we got heads 8 times, so on and so forth. And if we actually go ahead and run this, we can actually see that it forms that these values actually form a uh, fairly uniform distribution. So you see in the extremes where it corresponds to 0 and 10 over here, these values are the lowest, and that's obviously because we are like very, very, very unlikely to be able get to get tails 10 times in a row, and we're very, very, very unlikely to get heads 10 times in a row. And then as we get towards the middle, around where 5 is, that's where the values are the greatest. And that's because that's like what you're most likely going to do. You're expected, given 10 trials and flipping a coin is like with roughly half and half odds. You're expected that your expected value is that you're going to get heads 5 times. And so as we see here, it forms a pretty nice distribution, and it's pretty much as we expect. So that's really nice. We have attributes of a NumPy array. We explored some of this earlier on, but here's some of the different functions as well as other attributes which you'll probably want to pay attention to. So shape, it'll return the dimensions of the arrays. We explored this. Reshape will change the dimensions of the arrays. Do note that whenever you call reshape, the new shape that you specify must be equal to the total number of elements inside the arrays. So in this case, if we have this data over here, which is a 3-dimensional array, we have a total of 24 elements, and I call reshape over here. I have to make sure that all these values are equal to 24. And then we have flattened, which is kind of like a reshape, except it takes everything and turns it into a 1-dimensional array. We have size. This will return the total number of elements within the array. NDIM, I showed this off, shows the number of dimensions. And dtype returns the data type that is used within the array. So in this case, if we were to go ahead and run all of this, we see all these values, and you can go ahead and actually pause here to verify that everything matches up. But once you do, you'll see that everything is in its right place. We have indexing and slicing. So just like with slicing and indexing with Python lists, NumPy will allow for both basic as well as advanced indexing. And just like many Python lists and just pretty much most other programming languages, your index will start at 0 and not 1, and that's what we call zero-based indexing. Within a single dimension, you can index and slice by using the following, where we have x, y, z. So x is your starting index, y is your ending index, and z refers to our step size. So kind of similar to what we saw with arrange, with like start, stop, and increment. And yeah, note that if you don't specify a value for x, it's gonna assume that you're gonna start from like the start, and then if you don't specify a y, it's assuming you're going all the way to the end. And if you don't specify a z, the default is 1. So we have this example over here. This is a great visual showing off a 6x6 2-dimensional array. And we can go ahead and perform some indexing and slicing on this. So in red, we have, this is the equivalent of saying that we're going to get the first row by this 0 over here. And then we're going to call the comma to separate between the, like, one dimension between another. So we're getting first row, and then from that first row, we're gonna get the columns at indices, like between indices 3 and 5. Note that the indices, once again, the start is inclusive, but the stop is exclusive. And so when we say 3 to 5, then we're getting the items at index 3 and at index 4, but not index 5. And then we have this one in green. This is pretty much saying from index 4 all the way to the end for the rows. get all the columns starting at index 4 all the way to the end. And what we get is this square over here containing 44, 45, 54, and 55. We have this other one over here. This one's pretty interesting because we actually don't specify an X or a Y, or a Z for that matter. And so this is pretty much saying get all the rows, since we're not specifying an X and a Y. This is pretty much saying go from the start all the way to the end. So getting all the rows, and then from there get the column at index 2. So we get this column in blue. And then lastly, we have this purple one, where this one's the most complicated by far. But what it does is that we're going to select every second row and every second column. And the reason for that is based on these 2's over here. And so based on that, we're going to get every second row and every second column. But for the rows, we're going to start at index 2, whereas with the columns, we're just going to start at index 0. And so that's why for the rows we start at 20 and then 22, 24, rather than starting at 0, 2, and 4. If this particular 2, this x equals 2 value wasn't here, then 0, 2, and 4 would be a part of this, but they're not. And yeah, so that's an example of indexing and slicing. This is particularly useful if you do want to extract particular elements from it. But of course, if you want to get like individual elements, then you could also use the examples that I showed off earlier on, like this. And the good thing too is that I showed off a bunch of examples of indexing and slicing, and yet I didn't even mention that NumPy actually allows you to do negative indexing. And so this is really useful, because what this allows you to do is that it actually allows you to, whereas instead you're going from like the left to the right, or like from top to bottom if you're referring to like rows, this actually allows you to traverse the other way around. And so whereas instead of starting from, say, for example, it's like from this column all the way to this column, you're actually getting, by doing negative indexing, you're actually getting values from the end first, and then you're working your way backwards. And so that's really nice. And so, for example, I can go ahead and say that, for example, A. If I were to go ahead and call A at index -1, this is the equivalent of saying get the row where the index is -1. And in this case, the index with row -1 would correspond to the last row, which in this case is 50, 51, 52, yada, yada, yada. And then we have this other one. This one's a little bit more complicated, but we have our annotated comment over here. We say, in each row, get every second element in reverse order from the second to last column. And when we go ahead and do that, we go ahead and get all these elements, and you'll actually notice that they're in reverse order. And so that's pretty cool. And then lastly, we have mathematical functions. So like I mentioned, one of NumPy's greatest advantages is that you can do a bunch of complex mathematical functions with it. You might actually be familiar with the math library within Python, and NumPy kind of works in a similar vein to that, where you get to have a bunch of different mathematical operations. And so before I get to some of those mathematical functions, I would actually like to talk about some of the element-wise operations that you can do with arrays and matrices. So most of you should know that you can do just, 2 + 2 = 4 within Python. But you can actually go ahead and do what's called element-wise operations on arrays and matrices. So what this will do is that based on these given values, you're pretty much taking like the equivalent corresponding value between any two array or matrix, and you're performing like addition, subtraction, division, or anything like that on them. So for example, if we have this array A and this array, this matrix A and this matrix B, This is the equivalent of saying one. You could pretty much say 1 plus 5, and you'll get this top left element over here. Similarly, if we want to get this top right element, then we see our corresponding 2 and 6. 2 plus 6 is 8, and that works really nice. And we see that we do this for a bunch of other different operations as well. So plus, minus, multiplication, division, it all works out. One thing that is worth noting is that whenever we call this is not the same as matrix multiplication. So if you haven't taken linear algebra, this might sound a little bit confusing, but bear with me. Matrix multiplication is not the same as performing element-wise multiplications on matrices. And that's because the operation in which we perform matrix multiplication is a little bit weird. It really helps out with a bunch of the theory, again, in data science and ML. But the purpose of these videos is to talk more in depth about the functionality of a bunch of Python modules in which you'll want to be able to use if you want to compete in a bunch of the challenges. If you're more interested in the theory, again, I strongly recommend checking out course material like through stat courses and comp sci courses, particularly those with more so like ML data science backgrounds. But once you take a linear algebra class, you'll definitely be familiar with matrix multiplication, and you'll realize that this is not the same as performing, once again, element-wise. If you really want to perform matrix multiplication, then you can call np.matmul, where A and B are matrices. I won't spend too much time with the theory behind matrix multiplication. It is something that is very, very, very integral to courses like linear algebra and some of the theory behind machine learning algorithms. But once again, the purpose of these videos is to be able to teach you more so the implementation in Python rather than talking about the theory. And so I won't delve too much time into this. If you want to spend some time on it, then feel free and pause the video and try and take an understanding at it. And then lastly, we have some mathematical functions in which we can do. So once again, by default, NumPy will include a bunch of mathematical operators and functions that you can call at your will. So for example, we have np.sqrt. This takes a square root. We have natural log. We have a logarithm base 2, logarithm base 10, the power, exponents like e to the power of x, sine, cosine, tangent, as well as counterparts, arcsine, arccosine, arctangent, rounding, and then we have constants, pi, and Euler's number. If all that seemed like if all that seemed like just cannonball, spitball, and like you might not be familiar with some of these terms, like for example, arctangent, that's okay. The purpose of this is just to show off just a small sampling of some of the mathematical functions that are available. If you are interested in some mathematical function that might not be shown here, I would recommend checking the NumPy documentation because there's a very decent chance that it'll be on there. And yeah, you can run this code, verify that everything's correct, but yeah. And so that is pretty much a basic wrap through NumPy. It is definitely not a comprehensive, exhaustive, it is not an exhaustive 100% of NumPy, but it is at least a good enough base to be able to establish at least a small foundation of NumPy in which you can carry it on over into pandas. So NumPy and pandas, they often go hand in hand, and pandas will be what we explore in our next video. And so thank you for watching this video on NumPy. I hope to see you for pandas. All right, goodbye and happy hacking.